Okay, so hello everybody. This is a re-recorded version of the CP Masterclass Week 2. The original recording corrupted, so I'm just going to be going through everything a little bit quicker here. An email should have been sent out. If you didn't receive it, let Daeyoung or I know on the Discord. But yeah, so just to go through everything here really quick, just in case that anyone who didn't make the Masterclass still has the lecture available to them. So just a few announcements. First, we'd like to congratulate Ethan, Daeyoung, and Yuan for winning 4th at Montgomery Blair Informatics Tournament, or MBIT. Not yesterday, 2 days ago, actually. Um, they did a really good job. MBIT is a hard CP tournament, especially considering how many people participate. So this is really good, and we hope that other pioneers, a lot of which also went to the tournament, can continue to show these results. And also, yes, it is Hoko Hacks. Jesse isn't here, obviously, but Hoko Hacks is just a hackathon. It should have been plugged in your SEL lesson today. But you guys probably already know what it is. But in terms of CP, it's not that good for actual data structures and algorithms, but it's really good for language familiarity. So if you're feeling a little bit weak on Python or Java or whatever you choose to do in CP, and you're not like super familiar with it, Hoko Hacks is a great way to take advantage of a free opportunity to just go and code, as well as there's a typing competition. It's generally a lot of fun, and if you're not quite to that point where you can just learn an algorithm and already know how to implement it and stuff, this is a great opportunity for you to learn. Anyways, so today we're gonna learn about algorithms, and later we'll be going over specific tasks that there's multiple algorithms to solve. First, what is an algorithm? Algorithms are just step-by-step instructions that are used to solve a task. They actually aren't necessarily coding related, but they crop up a lot in coding and definitely a ton in CP, so they're good to know. So let's look at an example. So this is a problem we did in class. Obviously, I'm not gonna wait for you to solve this, but I encourage you to pause the lecture here and try this yourself. If you already know the optimal solution, I guess that's good. Just try to implement it in code if you already know that. And if you don't, try your best. If you don't know what the GCF is, you can just look it up, but just for reference, it's the largest integer that divides both A and B. Alright, assuming you've paused the lecture and I've given it a shot, here's the solution. There's actually more than one solution, but the optimal solution is called Euclid's algorithm, developed by a guy named Euclid. And the concept here is we start with two numbers, A and B, and we're assuming that A is greater than B. And we subtract B from A until A is less than B, right? There's still typos I haven't corrected from the initial masterclass, but that's okay. And then once this happens, we set A to B and B to A, and we keep on repeating that, so subtracting the smaller number from the larger number until we get either A is equal to B or that's going to equal 1. So an example of that implemented is we have this right here. You have 40 and 12. 12 is the smaller number, so we subtract that and get 28. This is still smaller, so we subtract. But now 4 is smaller than 12. So we keep on subtracting, and then we get to this point right here where 4 is equal to 4, so we know that the GCF is 4. And this is an example of that coded. I included a REPL link here because I encourage you to play around with this. There's a challenge. You can modify this to display the LCM instead of the GCF. This comes from a clever mathematical relationship between GCF, LCM, and the product of two numbers. I encourage you to try to figure it out by just trying numbers. If you already know it, that's great. You can just go ahead and code that. But yeah, you can't just use Euclid's algorithm directly, but there's a really smart way to get LCM from GCF. If you don't know it, encourage you to go on Stack Exchange or just Google this problem, and you'll see some pretty nice solutions. Alright, so now, when thinking about algorithms in general, obviously there's step-by-step ways to solve things, but in general with CP, the goal is to find the most efficient algorithm or the most efficient way to solve a problem. And there's two different types of efficiency that come up in CP and in general in computer science. First is spatial efficiency, spatial complexity, reducing the spatial complexity of a program. And in practice, this just means reducing the amount of memory that your program takes up. In actual computer science, there's four types of memory. There's input memory, output memory, file memory, and runtime memory. Input, output, those just have to do with the input that your program takes and the output that it outputs. File memory is just the amount of space the actual lines of code take up. And runtime memory is the amount of memory that your code takes up when it's actually running. So, for example, if we were to store some variables and input and do some calculations with those variables and store them in another variable, the variables you create during your program become part of your program's runtime memory. In CP, the only one of these that really matters is runtime memory, unless your file is like a gigabyte or something. That's a problem. But runtime memory in general is the source of major spatial complexity issues in computer programming. We aren't too worried about it right now, especially with the algorithms we'll be dealing with shortly. It's not too big of a deal, but just make sure that you were aware of the fact that you don't have unlimited memory. Both in real life and in CP, they'll limit the amount of memory your programs are available to you. So just be aware of this. But the more common issue with algorithmic efficiency is time efficiency. So this is pretty succinctly just concerned with minimizing the amount of time a program needs to run. It's the source of the dreaded TLE. The reason why TLEs are so dreaded is it means that there isn't just like a debug you need to do. You need to rethink your whole solution and optimize it, which is pretty hard, especially given the time limits of CP tournaments. So to avoid that, we want to start by optimizing our algorithms in the first place so we don't have to get to the TLE. So in terms of the time that algorithms take, we usually consider cases of time complexity. And what this really has to do with is we consider how does the time that your program take to run change with larger and larger inputs. So there's 5 major ones I consider here. There's obviously more, but those don't come up too much in CP. So first is constant time. Basically, just if you have no matter how much input, you could give your thing 1 line of input or a billion lines of input, it's still going to take the same time to run. This really never comes up in CP unless you've figured out a way to break the problem. If you come up with an algorithm with constant time that works, the problem you're doing is a bad problem, and maybe you should move on to another problem or something. Then there's logarithmic time. Program runtime scales with a log of the input size. This is one of the most ideal solutions that you can come up with in CP, and if you ever come up with an algorithm or an implementation of an algorithm for a task that uses logarithmic time, that's probably the solution that the graders are looking for. So just keep that in mind, and we'll go over some examples of algorithms that use logarithmic time. Then there's linear time, so program runtime scales with the input size. So for example, this would be like if your input got 10 times bigger, your program takes 10 times longer to run. This is pretty standard, but oftentimes when considering like potential solutions with nested loops stuff, you're going to get really far from linear time into polynomial time, which is program runtime scales with a positive power of the input size. So maybe x squared or x cubed. So if your program was 10 times longer, or if your input was 10 times longer, your program would take 100 or 1,000 times longer to run. Obviously, this is something we want to avoid generally. In bronze, in USICO bronze and silver problems, sometimes polynomial time solutions will work, but especially considering the size of the test cases that CP problems give, this is something we want to avoid. And finally, there's exponential time. Obviously, you can just tell from its name that this is something we really, really want to avoid. I can give you an example. If your program got like 10 times longer, if your input got 10 times longer, the program would take 1,000 times longer to run. But if it got 20 times longer, your program would take 1,000,000 times longer to run. So this is obviously really bad and want to avoid it at all costs. In general, we always want to aim for cases 2 and 3. And finally, there's this thing called big O notation. I didn't explain it here because it's really complicated, but in general, It just has to do with the complexity, time complexity of your algorithm in the worst case possible. So basically, when considering big O time, we subject your algorithm or the algorithm you're planning to implement to the worst possible case that it could possibly have. And big O notation just tells you, all right, if in this worst possible case, how long does your program take to run? But again, that's pretty much the same thing as this thing right here. You'll see big O notation a lot of the time when looking up different algorithms for, I don't know, research or just general studying by yourself for CP. So just be aware that it's basically this. And if you ever see big O n log n, that just means you're running in logarithmic time or linear, a combination of linear and logarithmic time. Again, these are all things that are highly Googleable, geeks for geeksable. So just be aware of that. And I have sent out a resources list in the email. So if you haven't seen that, again, contact DeYoung or I. All right. So for our Introduction to Algorithms class today, we're going to be looking at sorting algorithms. So obviously sorting is just sorting in a list or an array from least to greatest. This isn't really useful in competitive programming because of the sheer amount of built-in methods that exist in programming languages. For example, since we're considering Python, sorted is the built-in method, and sorted already is a highly optimized and like it runs in logarithmic complexity, so it's like really, really good. And it's not really worth your time trying to create a new sorting algorithm because sorted, chances are the built-in method is probably better than the one you're using. But sorting in general is a good start to learn about algorithmic thinking and specifically about optimizing time efficiency. So, challenge, create an algorithm to sort the list from least to greatest, just the sorting challenge. I would highly encourage you guys to code, especially since you're not timed or anything. You have about pretty much as much time as you want. If you're familiar with the optimal solution, try to code it. That's good for implementation. Obviously, you're not going to be coding this particular algorithm in CP, but it's good for language familiarity and getting used to that coding under conditions stuff. And for the last one, especially since this is recorded, pretty sure at least a quarter of you looked up the answer. Just know that Farmer John would not be proud. Okay. So assuming y'all paused this lecture and tried it out yourself, we'll move on to some potential solutions. So the first and most common solution that's come up with is selection sort, and let's go over what that is. Basically, you start with two arrays. One has input and one has output. The output array starts out as empty, and the input array starts out as whatever you inputted or whatever you set the initial array to be. So the general concept of this is you find the smallest element in the input array and you add it to the output array. And then you repeat that. This time, remember taking out the smaller element so that, it doesn't just default to the smallest element every time. And then eventually you can build up this array. It's kind of like if you had a row of books and you wanted to sort them alphabetically, right? You start by searching for, all right, which one starts with A? All right, which one starts with B, right? Or if you had a list of numbers, all right, where's 1? Where's 2? Where's 3, right? That's kind of what the concept of selection sort is, but obviously a lot more detailed and complex because, computers need like exact instructions. In terms of time complexity, selection sort has quadratic complexity. Didn't explain this in the initial class, but that's because you have to loop through this array multiple times proportional to the amount of elements you have. So that for this one, you only have to loop through the array 3 times, right? And for each of those, you have to make the length of the array comparisons to kind of check, like, all right, is this the minimum? Is this the minimum? Is this the minimum? And for 3 elements, it's not that bad because it's not too many comparisons. This is probably, 1, 2, 3, 4, 5, 6, maybe 6 comparisons or a little bit more depending on the nuances in your code. But if we went to 100 or 1,000, then the comparisons and the traverses are going to get really large really fast. So in general, selection sort isn't very good for scaling up because it has that, again, as we discussed, polynomial time. This is coded. This is a Python solution I came up with. Basically we have our array, and then the initial empty output array, and then we loop, and then here again this is the nested looping that I was talking about. In general, in CP, whenever you see nested looping, it's a sign that your algorithm or whatever solution you're trying to come up with isn't super efficient. So you should try to look for alternatives to what you're doing. But in terms of sheer, like, does it work or not? This does work. The nuances of the code are pretty standard, and you can go to Geeks for Geeks. I'm going to keep on saying Geeks for Geeks because it's a really good resource, or other websites, and they'll provide you detailed line-by-line breakdowns. And I included the REPL link, so you can modify this. You can play around with it if you want. And a challenge, you can modify this program to get input. So I started with an initialized array right here, but you can have it so that the user inputs these values. It isn't required, but it's good practice for CP because they'll never tell you what the test case is, and you can't just hard code it into your program. You have to try it out yourself. You have to get input, actually, my bad. So this is a good challenge for you all to figure out. Okay. So one other solution that people come up with is it's less common, but it still exists, and it's bubble sort. And I guess the main advantage bubble sort has over selection sort is that it requires less spatial memory, but it's really not that big of an advantage, and considering time efficiency isn't that big either. So it's not a big improvement, but it still is an improvement nonetheless. So the concept with bubble sort is we start with a single list, and then we traverse the list 2 elements at a time. And this doesn't mean like we go in pairs, so we don't go first element, second element, third element, fourth element. No, we go 1, 2, 2, 3, 3, 4, 4, 5. And because of this like incremental, like we're comparing twos, well, we're only going up by 1 at a time. This means that elements can be compared more than once, and especially considering the swap mechanism, which I'll talk about in a bit. Elements can be considered more than one time. So this does actually work in terms of a sorting premise. So what's the swap mechanism? Basically, we compare 2 elements at a time, and if the first element, which is supposed to be smaller than the second element in a sorted array, is in fact greater than the second element, then we swap them. Python has a really clean way to swap elements, which I'll go over like pretty shortly, but if you're working in Java or C++, you gotta introduce temporary variables, which is a little messy, but there's a lot of good resources out there to teach you how to swap elements, swap it really fast. There's actually ways that you can swap elements without a temporary variable, but that's a little bit too big brain for me, so I'm not going to go over it, especially considering the nice way Python has, which we'll look at in a bit. And so we keep on going through the list and making these swaps. But if we ever get to a point where no swaps are made, that means that the entire list is sorted. Because if no swaps are made, that means first element's greater than the second element, first element's smaller than the second smaller than the third smaller than the fourth, and so on. And then we just output the list. And then, again, this has quadratic complexity because we're traversing the list multiple times, and depending on how sorted or not sorted the list is, this could take a long time. I've included an example here that you can work through on your own time. Basically 10 switches with 10 doesn't switch with 11, but 11 switches with 7, and now this would be 7 and 11, and 11 switches with 9, so we get 10, 7, 9, 11, and finally 10 switches with 7, 10 switches with 9, 10 doesn't switch with 11 though, so we get 7, 9, 10, 11. We can see this is sorted, but the computer doesn't know. It has to go through one more time. 7 doesn't switch with 9, 9 doesn't switch with 10, 10 doesn't switch with 11. Obviously, this means no swaps have been made, so now we output the lists. And this is bubble sort coded. Same challenge. Modify the program to get input. But about that nice swapping mechanism I was talking about, this is the swap. As you can see, it says if a at I is greater than a at I plus 1. So if an element is greater than its next element, we swap them. And this is what the swapping mechanism looks like. I actually found this out pretty recently. It's really nice, it's short and sweet, and it's concise. And this sort boolean, this just loops through and says, alright, so far sort means true because we haven't made any swaps yet. But if we ever get to the point where we have to make a swap, then we switch sort to false. And then not false is true, so this while loop is going to keep on going. And then again, we talked about this. Two loops, not two loops, nested loops. That's not a great sign that your algorithm's very concise and efficient. So that's a sign that you might want to improve your algorithm. All right, and finally we have quicksort. So quicksort, this is really complicated. I'm gonna actually go into a draw tool to explain this. Let me just get a draw tool real quick. Sketchpad. Here we go. So let's start here. The general idea of quicksort is we split a list into two different lists, and then we split those two different lists into two different lists, and we keep on going until we hit lists of length 0 or 1, in which case we already know they're sorted, and there's no reason to even bother with running the code on them again. So let's consider an example. Oh god, this is not the thing. I am a professional. Okay, so let's consider 7, 10, 2, 4, 5. That's a pretty good array, right? So obviously this isn't sorted. It's pretty easy to tell. But, I'm actually going to modify this array a little bit. Let's call this 5, 4. Okay, cool. So the general idea of quicksort is we split this array into two separate arrays, and then we keep on splitting that. And this split is called a partition, and we'll get into the intricacies of coding that partition. So let's start. The first step in quicksort is choosing a pivot. And this pivot is going to be used to partition your array. I don't know, what's a random... Yeah, let's just choose 5. So we're going to pivot on 5. And what the partition function does is it creates two arrays. Let's create some arrays here. Oh, I'm drawing on computer. It is hard. One array is going to have all the elements in this list that are less than or equal to the pivot, and one array is going to have all the ones that are greater than. So we chose 5. So let's choose all the numbers that are less than or equal to 5. So 2 is less than or equal to 5. 5 is less than or equal to 5. And 4 is less than or equal to 5. And on the other array, we have 7 is less than or equal to 7 is greater than 5, and 10 is greater than 5. So we split our elements, we split our little thing, or partitioned it into two separate arrays. And now the partition function, or quicksort, tells us to repeat this. So let's repeat it. So let's choose a new pivot. Let's choose 4. So on this one, we're going to partition this into 2 and 4. Oh, that's wrong. There we go. So 2 and 4 are both less than or equal to 4, and 5 is greater than 4. All right. Now let's choose a random one. Let's choose 7. Oh, let's choose 7. So 7 is less than or equal to 7, and 10 is less than or equal to 10. Or 10 is greater than 7. My bad. Finally, these are all one element arrays. There's no point in pivoting these. In recursion, in the recursive algorithm for quicksort, there'd actually be a base case here that says stop, but this one is too long, and even though it's sorted, and this one was sorted as well, our program has no way of knowing unless it actually traverses the array. But as we'll see in a moment, traversing the array to check if it's sorted, it's actually not worth it in avoiding these base cases because of efficiency problems with traversing arrays multiple times. So it's actually a lot faster to just end up splitting the array. And once we've done that, right? So we have these arrays. So what do we do when we get a one element array? Now we have all of these are one element arrays. We just join them back. So let's join this one back. If we join these back, we get 2, 4. All right. And this one doesn't really join with anything just yet, so we'll just move it down. This is 5. This is so much effort. These two, there's not a tertiary thing, or I'll just merge them. So these two merge to 7, 10. And finally, actually these two first, my bad. These two merge to 2, 4, 5. And finally, these two merge to our final array of 2, 4, 5, 7, 10. So, as you can tell pretty succinctly, this is sorted. And you may wonder, alright, this was how many steps? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Even freaking Bogostar has less steps than that, right? So what's the point? The point is that this sort of divide and conquer method is super efficient when we get to larger numbers. Let's say we doubled the size of this array. Let's say we just doubled the size of this array, so times 2, right? This, or all of our other ones, like bubble sort and quick selection sort, they have quadratic complexity, right? So they're going to add like 4 times the steps as the original one. But this is just going to do an extra partition. It's going to do 1 extra step. It doubled the size of the input, but it's just going to do 1 extra partition. So even though the initial amount of steps is absurd, as you scale up, the number of steps you add to this initial amount of steps is really small. It doesn't actually increase all that fast. If we were to multiply this by 2,000, right? And in terms of quadratic complexity, what is that? That's like, what, 4 million more steps? This is going to take maybe 11 more steps, which is really, really good. Alright, and that 11 figure comes from natural log base 2, or frick, not natural log, I'm smart, log base 2 of 2,000, right? And this is around 11, right? And that's what the logarithm function is. You can just look it up, although a lot of y'all are in advanced math. I don't need to explain logs. But in general, that's where we get this logarithmic complexity figure from. It's actually, if we look at the big O, it's actually n log n. So I guess it's not quite logarithmic complexity. But in fact, this is the most efficient sorting algorithm out there. There's other ones like heap sort and merge sort, but this simple divide and conquer algorithm, which consider that it is the best sorting algorithm that everyone in the past 50 to 60 years of computer programming has come up with, is very remarkable. In terms of the sheer fastest, there's actually tiny, small ways to optimize this. That gets into like dynamic programming and even beyond dynamic programming, which is a little bit advanced for both this first class that we're doing on algorithms and CPN as well. Which is why, again, going back to this whole conception of sorted is an optimized quicksort. I think what it does is, like, if the size is like smaller, like if you get to a small enough size, it switches to another sort where, like, maybe merge sort or heap sort or a heap sort or something like that. The details aren't super important, but in general, in competitions, if you ever get that to happen to you, just use sorted. You'll save a lot of time. Finally, quicksort coded. This is actually incomplete code, so I'll just go to Geeks for Geeks. This is actually good. This is a good preview for Geeks for Geeks. As you can see, I've already looked it up. So there's a good explanation, probably better than I could give. It gives you pseudocode, example, and finally we have solutions. And in general, in this class, we want to always look at the Python solution, unless you're using Java, right? And this is the general scope of the code. right? So if we just walk through it, this is the initial call of the function. So we have our little test array. Again, you could modify this to make the algorithm get input, but it's not necessary. Then we just get the length of the array, and then quicksort the array that we're using 0 and 1. Now, what are these 0 and n minus 1? These are actually consequences of the partition function, right? Because in partition function, what we are forced to do is split up this array into two separate arrays. But what this program does is it actually doesn't split the thing up into two different arrays, but it gives two separate indexes to work with. So although it looks like it's the same array that's being quicksorted, it's not really, because we're looking at two different scopes of the code. And I don't know why it's called pi. But if we were just to walk through this code, we have initial call 0 to, what is that, 6? No, yeah, 6 minus 1 is 5. So then if we go, we partition this array at low and high. And this goes back to the pivot logic we were talking about how, you know, if it's less than the pivot, you do this. And since this code is only using one array, it utilizes swaps. So this is the swap logic we were talking about again. It's really useful, so you should try to use it as much as you can. And what it ends up doing is it swaps elements so that all of the ones that are less than a pivot are on one side of the code, and all the ones that are greater than the pivot are on the other side of the code. And then it does that. And this is really smart, because notice that if we look at the indexes, it actually skips over this pi index that we were talking about. That's intentional, because although the way we partitioned it to make it a little bit simple was to keep the pivot in one of these arrays, this can actually become problematic if we're trying to split arrays. So if we're trying to choose pivots, because I chose the pivots conveniently so that we wouldn't be stuck in infinite loops. But just say that we had let's just say we had instead of 7 and 10, we had 10 and 7, right? And then I chose 10 as the pivot, and again, less than or equal to and greater than. We would get 10 and 7. This would split into 10 and 7, and a blank array, an empty array. And then this just loops back, because the partition function works on this. And then you get infinite loop right here. And this is by far the worst thing that could ever happen to your code. So it actually leaves the pivot where it is. And because of the nature of the code and how everything to the left of the pivot stays in its own array, and everything to the right of the pivot stays in its own array, the pivot is actually already where it needs to be. So there's no need to create a new array or anything. And then this sub function becomes smaller, and then we run it here. We rerun quicksort on that, but now low and high have changed to low and the one before the pivot, or the one after the pivot, and high. And this logic just keeps on running and running and running and running. All right. One fun fact about quicksort actually is that its worst possible case, the way it calculates O n log n, remember going back to that worst case scenario, is actually with the sorted list. So if array was already sorted, quicksort is going to take the longest it ever will, which is pretty funny. But again, there's no way to check that, because by checking the array initially to make sure that it's sorted, you add to the complexity, and we would move from logarithmic complexity to quadratic complexity, which defeats the purpose of quicksort itself. So yeah, that's quicksort, and that's actually the end of class. I don't think I have any more slides. Resources page is not filled yet. But again, everything you'll need will be sent out in that email that you should have received by now. If you haven't received it, it means that you aren't on the mailing list for Pioneers, which you need to be on, so contact Dayoung or one of the board members. Or I haven't sent the email because I'm lazy, in which case it will be coming out shortly. But besides that, thank you for coming, and hope to see you next week. Bye.